So let's say we just talk about the extreme values and settle points for the two variable functions. So that means it's just a service. Z is equal to f of y. So we also define what is the local maxima value and local minima value. So I think it is quite easy to extend the idea for single variable function to two variable functions. Because for single variable function, we just uh, we just take care of open interval. But for we just focus on an open interval. But right now it's a two variable function. So of course the domain will lay on in the xy plane. So that will form a 2D two-dimensional area. So in the past, maybe for single variable function, we just focus on x-axis. So of course, we just focus on open interval, single variable, right? But right now it's a two variable, so we just focus on a plane region. So in this case, if we say f of ab is can provide a local maxima value, then any point surrounding or neighboring its neighbor AB will just provide a value which is less than f of AB, so that we will say f of AB is provide a local maxima value. Okay, so similarly for the local minima value, if f of A prime B prime provides a local minima value, that means its neighboring point that provide a value larger than f of A prime B prime. So this is a maxima value. This is for the minima value. But so we also define what is a critical point. So if partial f partial x is equal to 0 and partial f partial y is equal to 0, or one of or both of them does not exist, we will define it as a critical point. So if you cannot accept the idea just right after the definition, then you can also just think about when we just face the critical point for single variable function, we also have a similar definition. For example, if f prime of A is equal to 0 or f prime A does not exist, that means f prime A is a vertical, is a positive infinity or negative infinity, then we will say f prime A does not exist. So for two variable function, we also have similar definition for critical point. So something like that. And for the two variable function, there is a very special point. We call it saddle point. For the saddle point, for some direction, you can find it just provide a local maxima value. For example, if you just follow this path, you can see f of AB provide a maxima value. However, if you just follow this path, its corresponding value, you can see f of AB just provide a local minima value. So in such a case, we will call it saddle point. So saddle points, it cannot provide local maxima value or local minima value, but just for some special paths, it can provide. But for the open region, you cannot say it just provide maxima value or minimum value. Okay, then we just learn this one. This is the very important part. So if we want to distinguish if at some point it just provide local extreme value, we can just use its second derivative to test. So that means if f of y and its first derivative and second derivative partial derivatives are continuous through one disk, which is centered at AB, then if its partial f partial x is equal to 0, and partial f partial y also is equal to 0. So did you remember when we just face the single variable function, we also do that, right? Because we try to find at which point its first derivative is equal to 0. Then at that point, the point will be the candidate, which provides the local maxima value or minima value. But it doesn't mean it just can provide it, because it's just a candidate. It's just a possible point to provide the maximum value or minimum value. But we can just treat it as a candidate and then try to see if it will just the local maximum value or local minimum value will happen at that point. So there are some rules to check. So we can check the discriminant first. This is about this one, okay? Partial f, partial x times partial f, partial y minus partial f, then partial f, partial x, partial y squared. You need to check if it is positive. If it is positive, then you can continue to check. If partial f, partial x is less than 0, then we will say at this point, AB, it will provide the local maximum value. So similarly for this one. But if the discriminant is less than 0, that means it's negative value, provide a negative value, then we will say it's just f at this point. At this point, it's just the point is a saddle point. Okay, but if unluckily the discriminant is equal to 0, then we will say it's inconclusive. We cannot decide if at AB some extreme case just happened there. Okay, so this time I just provide an example here for your reference. So today we will continue to extend the idea. So today we will focus on absolute maxima and minima. But this time we focus on cross boundary regions. So what is cross boundary regions? Did you also notice that in this case, actually all xy plane belongs to any point on the xy plane in the xy plane belongs to the domain for this function. So this is not a cross boundary region. But today, here, we just want to focus on cross boundary region. So I just list the rule for your reference first, and then we look at a simple example. Then we just follow the rules and then check where we can just find the maxima value and minima value. So the first thing we need to do is please just list all interior points of R. R means the region, okay, where F may, please follow, may have a local maxima or minima value. This is just for interior points. And the second part is please just list the boundary point of R where f of sy may provide a local maximum minima value. Then the last part is we need to look through the list for the maximum and the minima value. Of f. Actually, we just did that before. Did you remember for single variable function? For single variable function, we did that before, right? For example, if I give you y is equal to f of x, so what thing we will to do first? The first thing we need to do is, okay, for example, if we just focus on A and B, right? So if A is here, B is here, so these 2 points will be the candidate to provide the maximum value. These 2 endpoints will possibly provide the maximum value and minimum value. But at the same time, we also need to consider, for example, if f prime x is equal to 0, if it is differentiable and it is an interior point, so we will also focus on these 2 points. Then see, for in this case, maybe these 4 are our candidates. Then we will check which one will provide the maximum one and which one will provide the minimum one. Then finally, we can find the absolute maximum value and the minimum value. So this is for single variable function. So for the 2 variable functions, we also focus on a closed boundary region. Just like here, we just focus on a closed interval, right? For single variable. But for 2 variable, we focus on closed boundary region. Okay, so the possible point could be the boundary point, right? With the boundary point, and also could be the interior point. Just like here, for single variable function, the point which can provide maximum value or minimum value could be the endpoint or the interior point, which just satisfy these 2 points are the critical points, right? Endpoint is also the candidate. Okay, then finally just read through for the maximum value and minimum value. Okay, so let's just start by an example. Please just find the absolute. The so-called absolute is just global, not just local. Absolute maximum and minimum values of f. Then f of xy defined as 2 plus 2x plus 2y minus x squared minus y squared on the region bounded by s is equal to 0, y is equal to 0, and y is equal to 9 minus x squared. 9 minus x. So you can see this is a add-on. This is an extra condition. If we just hide this part, if we just hide the green part, then we will just go back to the example like this one. You can see here, we didn't set any restrict to the region, but here, we just follow these 3 lines to restrict the region, right? 所以当然先把题目确定哦。上礼拜讲的这个题目呢，它没有限制任何的条件，所以它的很天生的这个定义域呢，就在 xy 平面上面，对不对？我没有限制在哪里。那现在呢，这个题目呢，多了限制在 s 等于0 y 等于0跟这条斜直线，所以大家可以想象，过去我可能看 xy 平面上面的任何的点，但是我现在只看这个 boundary。OK， 那就会跟这个单变数的时候一样，如果我限制你的 boundary， 很有可能发生极值的地方在哪里？一种在你的边界上面，另外一个是在你的内部的点上面。啊，内部的点我们可以用那 critical point check， 对不对 ？Okay, so let's start to solve this problem. So if f of y is equal to 2 plus 2x plus 2y minus x squared minus y squared, then the first step, we just try to list the interior point. So, okay, first part we just focus on interior points. So we need to focus on this is s is equal to 0. This is x equal to 0, right? Then this is y is equal to 0. Then this is y is equal to 9 minus s. So the region we will focus on is here. Not the whole xy plane, right? We just focus on this boundary region. We not like previous one, focusing on the whole xy plane. Okay, so the interior point, if we want to focus on interior point, so we must find, okay, is there any candidate just happen within the region? So for the interior point, what we need to do is to find where partial f partial x is equal to 0 and partial f partial y is equal to 0, right? So if we calculate partial f partial x, it will be 2 minus 2x. I believe you can do that yourself, right? 2 comes from 2x. Minus 2x comes from negative x squared. So when we calculate its first partial derivative with respect to x, it will be 2 minus 2x. Then partial f partial y is also, right, similar. So if we let this name become 0, then we can get sy is equal to 1, 1, right? So easy, right? Because these two functions, these two equations, we need to simultaneously meet the requirements from these two equations. So the first point we need to consider is 1, 1. So 1, 1 is here. This is 1, this is 1, 1. Then we can continue to check partial f partial x is equal to negative 2. Then partial f partial y is equal to negative 2. Then partial f partial x partial y it will be 0. So we can get the discriminant by -2 times -2 minus 0 squared. So maybe I just note it down here for your reference. And this is the discriminant, right? And we can see the number is 4. 4 means positive, right? So positive, we just remember that if positive, the condition will just fall into 1 or 2, right? Then we need to continue to check partial f, partial x, partial x, or it could be negative or positive, right? So then we can continue to see that this one is negative. Then here is positive. So we can conclude that 1, 1 can provide a local maxima value. The value is 4. Because you can simply use 1, that means this comes from f is of 1, 1. Okay. So this is the first point we need to consider coming from the interior point. But of course, once you get 1, 1, you need to check if it just fall into the region. If just out of the region, you don't need to take care of it. Understand that? 如果你用这个一次微分，一次偏微对 s 偏微对 y 偏微等于0去取得这个点是1，1的话，这个点刚好有落在里面了哈。那如果它没有落在里面，这个就不用管它了，因为你的区域，你现在区域呢，你只 focus 在这一段，了解吗 ？Okay. Then after interior point, the second step is boundary point. So then we continue to focus on the boundary points. So for boundary point, you can see for boundary point, this is a boundary point. This is also boundary point. This is also boundary point, right? So we need to consider 3 cases. The first case is on y is equal to 0. Let me just draw the figure here again. So right now, we focus on y is equal to 0. This is s equal to 0. Then this is y is equal to 9 minus s. So right now, we focus on any point in these 3 lines. Okay. So if the boundary just happen on y is equal to 0, so y is equal to 0 is here. Is this one. Right now we focus on this one. For this case, then we can get f of xy is equal to f of x, because right now on this point, on this line, any point for any point its corresponding y value is 0. So the function will become 2 plus 2x minus s squared. Then s will restrict between 0 to 9. Why is 0 to 9? because you can see 0 comes from this point, 9 comes from this intersection. So with this x equal to 0, y is equal to 0, we can have an intersection 0, 0. Then this is 9, 0. This is 0, 9, right? So you can see, you can easily to get the intersection. Here is 0, 0. Here is 9, 0. And then this is 0, 9. So that's why x will be retrieved on this interval. Okay, so did you just notice, originally this is a two-variable function, right? But since y is fixed, y is 0, because we just focus on the point, y is equal to x, y is equal to 0. So all y value should be 0. So we just reduce the two-variable function into a single variable function. Now with this retreat, did you remember I just reviewed the concept to you? For single variable function, this is a single variable function. We just focus on the boundary and also its critical point. So right now, we just focus on a single variable function with this constraint, with this cross interval. So then we can continue to differentiate f from s of s0 is equal to 2 minus 2x. So that we hope it can be 0. Then we can find s is equal to 1. So by this one, s should be 1. X should be 1 here. Right? So this will provide this one. Then plus 2 endpoints. This will focus on this one and also this one, right? So that we will just consider 3 points. One is the 1, 0, 1, 0. This is the interior point for this interval. And we also need to consider 2 endpoints. This will be 0 and 9. So right now in this case, we need to consider this one, and also this one, so that we can get f of 0, 0 is 2, f of 1, 0 is 3, f of 9, 0 is negative 61. So finally, these 3 points will provide these 3 possibilities. Okay? Don't worry, we can just focus on the second one and practice again. So this is this case. So the second case, if on s is equal to 0, so we can follow the similar step that f of sy, in this case, s is fixed, but y is variable, so that we can get 2 plus 2y minus y squared, then y also is restricted to 0 to 9, right? So this time, we will focus on this part, right? This time we will focus on this part, just so following the same way, we can just differentiate it. So okay, we can get f prime of 0y is equal to 2 minus 2y. 2 minus 2y. We hope it can be 0, then we can get y is equal to 1, right? Then in this case, y is equal to 1, then we can get the point will be 0, 1, right? So we will focus on this one, 0, 1, right? Here, this point will be located here. Then also plus 2 endpoints. The 2 endpoints will be 0, 0, and also 0, 9. So that will be here 0, 0, and 0, 9. One is 0, 0, one is 0, 9, right? So in this case, in this line, these 3 points are the possible candidate, so that we can continue to get f of 0, 0 is equal to 2, f of 0, 1, 0, 1 here, 0, 1 is here, then the e is also 3, and f of 0, 9 will negative 61. Okay, so for the case 1 and case 2, they are quite similar. The only difference is one is focused on x-axis, the other one is focused on y is equal to y-axis. Then the third line, the third straight line is y is equal to 9 minus x squared. So right now we will focus on the point in the line, in this line. Okay, so for the third case, this time we just focus on y is equal to 9 minus x. We focus on this one. So in this case, we just focus on f of sy, then f of x, then y is 9 minus x. Right? You can see for y part, we will transfer it into 9 minus x squared, 9 minus x. Then we just use it for, then we can put it to the original function is 2 plus 2x plus 2y is 9 minus x, right? Plus minus x squared minus 9 minus x squared. So you can see the original y will be replaced by 9 minus x. Right? This is 1, this is 1 squared. Then through some calculation, you can get the result is negative 61 plus 18x minus 2x squared. So you can see the function finally will be converted as this one. So this is a single variable function again, right? We just reduce it as a single variable function. So we can continue to differentiate it. We hope it can be 0. Then we can get s is equal to 9 over 2. then we can also get if x is equal to 9/2. So we just use it as the input for this problem, then we can also get y is equal to 9/2 and plus 2 endpoints. So what is the 2 endpoints? Okay, this time you can see this is the first point, right? So the first point 9/2. So we can get here. Or maybe I just use this one shape. This is 9/2. This is 9/2, right? This is the first point. Then 2 endpoint. 2 endpoint will be here, right? The triangle and this one. So for this line, we will focus on 0, 9, 9/2, 9/2, and 9, 0. These 3 points. So we will focus on f of 0, 9. It will be -16. There's 61. And f of 9/2, 9/2, it will be -41/2. Then f of 9, 0, it is -61. So let me just make it smaller. You can see right now we have 9 candidates, right? For the first line, I mean, y is equal to 0. Maybe I just make it smaller. Okay, it's still. So if we just focus on y is equal to 0, it provides these 3 points. It provides these 3 points, right? If we focus on x equals to 0, these 3 points are candidate. This one, then this one, right? If we focus on y is equal to 9 minus x, we will focus on these 3 points. Of course, some of them just duplicated, right? For example, 0, 0 or 9, 0 is just duplicated. They are just duplicated. But in total, maybe we just need to just take care of these 9 points, even though some of them just duplicated. So you can see this is 2, 3, -16. So then this is 2, 3, -16. Then -16, -41/2, then -16, 61. Don't forget, we still have this one, inner point, right? So don't forget, we still have one inner point here. This is 1, 1. Coming from here. In this case, f11 is 4, right? So we need to check 4, then this, and also this. So finally, we can conclude that a maximum value is 4. A minimum value is -61. This is at 1, 1. This can be at 0, 9 or 9, 0. Okay, so finally, this is our final result. So you need to check all candidates, and finally find its maximum value and minimum value. 哦，这个题目讨论起来有点长哈、哦。那回去以后呢，我有挑一个题目，它是四边形的。那四边形其实老师做简单的，学生做困难的，或者老师做那个线段比较少的，学生做比较长。四边形它就有四个边，你就要四个去考量它 ，x 等于y 等于，啊，另外再有一个 x 等多少，y 等多少，你就这样逐一个去讨论。每一个边界上面一定可以讨论出几个点出来。最终呢，就如这个题目一样，把它全部加总在一起，这边界上面的。但是不要忘了，它也属于内部的这一块。内部的点就是我们刚刚学到的这个，用这个二阶偏微分搭配这个它的这个判别式，先去判断出这个点到底有没有提供了极大值或极小值，对不对？用这种方式呢，来找出这些可能的点。那最后呢，把这10个点，这里有3个，这有3个，这有3个，跟这个点，当然这3个里面呢，是有些都重复了，事实上它只有1、2、3、4、5、6个点而已。因为它边界点刚好2个都重复，所以基本上呢，有些是重复算了。但不要忘了，你内部这个点还要找回来，因为它有落在这个区域里面，最终就有这7个点来考量，那最后去判断出谁是最大，谁是最小。Okay, so this is for this section. So I will list the question here. Okay, then we just move to session 8. We will talk about the Lagrange Multipliers. For Lagrange multipliers is also very important, but I will just teach you how to use the Lagrange multipliers method. I will not talk about why it can be done by this way, but later I will show you an example. That example somehow can just show why Lagrange multiplier will just behave like this. Okay, then before that, I also want to show you that you can see for this case, I give you a function, right? I give you a function, then I give you a triangle, or even for your when you go back to home, you take some exercise. I give you an example that this is a rectangle, this is a triangle, but the boundary is a line, is a straight line. For this case, there are 3 straight lines for this boundary region. For the exercise, I ask you to do the exercise for that example. That example just retrieved by some rectangle. But no matter triangle or rectangle, the boundary is composed of by several straight lines. Okay, but easy for you. You can easily to find the boundary, then find the boundary point to see them as an example. But in this case, I will show you the first example that if I give you f of xy is equal to like s cubed minus s1 minus y squared subject to s squared plus y squared is equal to 1. Then what's the maxima value? What's the maxima value? What's the minima value? So similar to this one, right? Similar to this one. I give you the function. I give you the retreation. The retreation is defined by these three lines. But in this case, the region is subject to. Subject to means the constraint. This is constraint. So that means any point on the circle, I just want to know at what point that can make the function have a maximum value or minimum value. But for this case, this is straight line. It's easier. But this is a circle. One way is you just try to list all possible points and then calculate its function value, and then compare the function value. Then finally you can pick the maximum value and the minimum value. But it's impossible, right? Because we have infinite numbers of points from this circle. So we cannot do that, right? So in this case, we need to rely on Lagrange multipliers to solve this problem. So this is the background, OK？ 这背景是什么哈？我们在休息之前先把背景讲清楚。刚刚在13至7的时候讲的就是什么？从一开始不限制任何区域，就是那个domain是 xy 平面上面任何一个点。好，慢慢的我就把线缩到哪一个三角形，或者回去以后，请他回去做的是给你一个矩形，不管三角形也好，矩形也好，怎么样？它限制的区域或者点都是直线上面的，所以你很容易用我刚刚什么用 y 等于x 啊去取代掉，变成让函数变成一个单变数。所以回到单变数简单，对，一次微分为0的点就是我们在意的点，对不对？好，但是13至8告诉我们这个Lagrange Multipliers， 它一样要我们在算什么？求极大值，给你一个函数，对不对？也给你一个限制条件，这限制条件刚刚讲的，我要限制在这个三角形里面，或者三角形上面哦，或者这种矩形上面哦。但是呢，这个不是直线，我们不可能像刚刚那样子又把它带掉，对不对？变成单变出来弄，所以它的限制变成是一个圆形上面的点，或者是什么那个椭圆上面的点。那这些点有无穷多个，你不可能每个点都拿出来。去带到这个函数上面去取出它的极大或极小。那这个时候呢，这种 case 呢，你就用这种 Lagrange Multipliers 的方法来解这个问题。我们先休息一下，回过来看怎么样做这个问题哈。So right now you already know why we need Lagrange multipliers, right? If we just face the problem and its constraint is not a straight line, we need to follow the mechanism of Lagrange multipliers. So right now I always just write down its rule. Suppose f of xy z. This is a 3-variable function. This is a 3-variable function, but it's fine. If you just go for 2-variable function, it's also fine. Okay. suppose f of yz and g of syz. So just remember there are two functions. One is f, one is g, the other is g. We assume they are differentiable. To find the local maxima or minima values of f of syz subject to the constraint g of syz is equal to 0. Try to find the values of syz and the lambda. There is an additional variable lambda that can simultaneously satisfy gradient f is equal to lambda times gradient g. So this is the rule, and later I will show you how to do that, and then I will use one example to show why gradient f should be equal to lambda times gradient g. Okay, so let's just introduce carefully one by one to you. So just notice that you will be given two functions. One is f, the other one is g. Okay, then f is your target function. You want to evaluate its function value, but g of syz just provide the constraint. Okay, so two types. One is your target, one is your constraint. Subject to means constraint. So we just try to find f of syz. Can f of syz provide the local maxima value or local minimum values? But the constraint is g of syz is equal to 0. So in a very tuition way to explain the idea is all point syz meet the requirement g of syz is equal to 0, and you just pick all point syz to f of x to as an input for f of syz, then see what is the maximum value and what is the minimum value. Can you understand that? 好，这很重要。我们这边讲慢一点哈，这一步一步大家搞清楚它的角色扮演的关系。如果你要用 Lagrange Multiplier， 它呢，第一个前景告诉你，如果它不是那种规规矩矩的直线的时候呢，这时候呢，你就需要用它，用 Lagrange Multiplier。那你如果看到上面给你的例子里面，你会发现，我事实上也是有个 target function， 叫做 f of xy 等于 blah 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 x blah 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 y 的，对不对？这是我的目标函数。但是呢，我会受限于谁呢？受限于后面那个，我用绿色框起来这个，对不对？那代表什么？我的点啊都要满足 x 平方加 y 平方等于 1。所以比较白话来讲，以上面这个例子来讲，就是我的点啊受限于 x 平方加 y 平方等于1，受限于它这个点一定要在圆上面。那这些点呢，我想来评估这个 f(x,y) 有没有哪个点让 f(x,y) 得到了趋的极大跟趋的极小值？好，那我们把它 generalize。假如这是一个3个变数，这样讲这是2个变数，有没有？你会发现这是2个变数，这也是2个变数。如果我把它变成一个3个变数，其实它的想法是一样，就是你总是会有一个什么 f(x,y) 你要来评估它的函数值多大多小。但是呢，它受限于 g of xyz， 所以你的目标是 取得 f of x y z 的极大或极小值，但是你的受限的点，那些点受限于它必须让 g of x y z 等于0，这样懂我意思吗？所以你可以想象这个点一定是一个什么点？空间上的一个点。空间上有无限多，不一定无限了，就很多个点，这些点啊要完全满足 g of x y z 等于0这个条件。但是你把这些点全部挑出来之后呢，把它放到函数 f of x y z 的 x y z 来，每个带一个就取一个值，带一个就取一个值，你能取得它的极大或极小值。这是这个题目的命题。好，千万把这 f， 所以我在写这个给大家看的时候，你会发现我用2个不同的颜色，你一定要把它2个角色的半圆确立出来。好，绿色是你的目标函数，我希望它最大或它最小。但是黄色的呢是来限制你那些点的。好，那怎么做呢？做法就是你去找出 x、y、z， 还有一个lambda的值，他们同时要满足这个 gradient f 要等于 gradient g and I forgot one and g of x, y, z is equal to 0. Gradient f must be lambda times gradient g, and g of x, y, z must be 0. So did you just notice? Did you remember gradient f is a vector, right? Gradient is a vector. Gradient g is another vector. If one vector is equal to constant times is another vector, actually these two vectors are parallel. 这2个向量 gradient 是一个向量，这个也是一个向量，这2个向量等于某个常数相乘，这2个向量怎么样？它一定是叠在一起的，对不对？它们一定在同一条线上，只是什么差别？只是一个乘以lambda倍而已。等一下我讲，为什么刚好哦？下面一个例子非常好解释哈，只是它恰巧，但是因为这个比较难去理解嘛，所以只告诉大家怎么做。但是理论的部分呢，我们课本上有稍微提一下，但是我等一下用那个例子来解释为什么gradient f 要等于gradient g 的一个lambda倍，同时 g of x y z 要等于0，用这个跟这个联立起来之后去取得 x y z 的lambda。Okay, so I just give you an example. Find the greatest and smallest values that the function f of xy is equal to xy take x squared 8 plus y squared over 2 is equal to 1. So did you notice that you can see we have a target function f of xy is equal to xy. We have a constraint function coming from this one. So you can see, you can just regard this. You can use this to get your g of xy is equal to 0. So let me just, you can sub it as, okay, right now f of xy is equal to xy. Then g of xy, I can define it as x squared over 8 plus y squared over 2 minus 1 is equal to 0. So please make a comparison here. You can see This is the other target function, f of sy. Here, f of sy is sy. Subject to the constraint g of syz is equal to 0. So we have a constraint function is this one. Is this one, right? So right now we already have f, we already have g, right? And we start to calculate that, so that we can have gradient f is equal to y I plus xj. We also have gradient g is equal to 1 for x I plus yj. So as requested, gradient f must equal to lambda times gradient g, so that we can get here, this is x part, this is x part, this is y part, right? So we will have y is equal to 1 over 4x times lambda. And we also have s is equal to lambda times y. Right? Because this is gradient f, this is gradient g. So if we have gradient f is equal to lambda gradient g for x part, they will be proportional. For y part, they also will be proportional, and the ratio is lambda. Lambda should be white. Okay. So by this one, we can get y is equal to 1/2 lambda times lambda y. Right? Y is equal to 1/2 lambda times x, right? But if so, I cannot sub x and y. But x is equal to lambda x, y, so I should use it as this one. Okay? Originally, there are three variables, x, y, and lambda. But right now, through this conversion, we can get it will be y is equal to this one. That we can continue to get 1 over 4 lambda square y minus y is equal to 0. So that we can have y times 1/2 lambda square minus 1 is 0. Then we can get y is equal to 0, or 1 over 4 lambda square is equal to 1. So finally, we have these two possibilities, right? But for this case, for case 1, y is equal to 0. If y is equal to 0, since x is equal to lambda times y, so x is also 0. In this case, x is 0, y is 0. Is now a reasonable solution. because 0, 0 is not, you can see 0, 0 is not on this curve, right? It's not on this curve. The second one is 1 over 4 lambda square is equal to 1. So that we can get lambda is equal to positive 2 or negative 2. Right? Because you can easy to move 4 to the right hand side, so the lambda should be positive 2 or negative 2. Right? So we can get S is equal to 2y, or S is equal to negative 2y, right? Because of this one, S can be 2y or negative 2y, negative 2y. Then just use this one, we can get S squared 2y squared over 8 plus y squared over 2 minus 1 is equal to 0. So that we can get y squared over 2 plus y squared over 2 minus 1 is equal to 0. So that we can get y is equal to positive 1 or negative 1. Right? Because y squared is equal to 1. So y is positive 1 or negative 1. So in this case, we can continue to get S is equal to positive 2 or negative 2, right? Because S is equal to 2y. So when y is equal to 1, then we can get S is 2. If y is equal to negative 1, we can get S is negative 2. Right? This is one possibility. Then for this part, negative 2y squared plus y squared. So it's all the same, right? Actually, it's all the same because this is square. So finally, the solution is the point S could be, for the point S could be the SY pair can be positive 2, then S is also, so 4 combination, right? And positive 2, negative 1, then negative 2, positive 1, then finally negative 2, negative 1. So 4 points. And 4 points, you can cause maximum value is 2 and minimum value is negative 2. For these 4 points, the maximum value, if you remember, the target function is S1. Make it smaller. The target function is f of sy is equal to s times y. So the possibility is 2 times 1 positive 2 times negative 1, negative 2 times positive 1, or negative 2 times negative 1. So finally, the maxima value will be 2, and the negative, this is the maxima one. This one can produce a maxima one. This one also can produce a maxima one. And the green one can produce the minima one. This one is maxima. Okay, so this is the solution to get the answer. Don't worry, later I will explain it again. But I just want to use this case to explain why the gradient vector will be the gradient vector. These two gradient vectors will be parallel. I will show you. This S, this Y. Okay, so let me just this is our constraint function. It's an ellipse, right? This is our constraint function. This is S squared over 8 plus Y squared over 2 is equal to 1. This is our, so we can convert it to get G of SY is equal to this one. I already mentioned this part earlier, right? This is our G of S function. And our target function is f of SY is equal to XY. So we just want to know that which point can maximize the f of x value, right? But you can also notice that I just draw some figure for your reference that if this curve is sy equal to 100, and as it get closer to, for example, 1.5. Okay, so for example, if this is sy equal to 50, something like that, and this is for some extreme case, maybe I didn't draw it quite well. If this is sy is equal to, for example, 1, and this one is sy equal to 0.5, something like that. Okay, so we know if sy, all this curve is about sy is equal to c. So if sy equal to 100, as s increase, y's value will decrease. If s value is decreasing, y value will increasing, right? If you just follow this, any of them, sy is 100, sy is 15, sy is 1, sy is 0.5, all of them, if they just follow sy is equal to constant, you always can find that on either curve, you always can find as s increase, y is decreasing. S decreasing, y is increasing. Is that okay? 好，我们一步一步来哈。这个例子呢，大家有没有看到？我们的目标函数是 s1，那我的 constraint 是在这个点上，这条线上面的点，黄色的点，我想要知道说，把这点啊带到 s1 可以得到几，最多什么样的值，最少什么样的值。但是呢，我们来不妨观察一件事情 ，sy 等于7这种曲线，但是它都有一个共同的性质是什么 ？sy 等于100，还记得 level curve 吗？对吧？这两个相乘出来是100，代表什么？这条线上的点啊，当 s 增加 ，y 一定减少 ；s 减少 ，y 一定增加。 这个没问题吧？对不对？任何 sy 等于 c 的曲线都有这个特质。到目前同意，对不对？好，那 sy 等于100啊 ，s 等于50啊 ，sy 等于1啊 ，sy 等于0.5。大家想一想，这个 sy 等于100的时候，它这个点啊，这个上面的线啊，跟这条曲线，跟这个抛物线，这个椭圆线呢不会相交，但是呢，到1的时候呢，好，它跟它相交这个点，来，大家注意看这一点哈。The intersection here. So if this point is the intersection of this ellipse and sy is equal to 1. So can you tell me if I just use this point as the input for this function, what's the return value? 1. Why 1? Because this point sy is equal to 1 just is passing by, right? But so you just use this point. Maybe you cannot exactly know what the point is, but since it's a passing sy is equal to 1, so the return value should be 1. So similarly, for this point, the orange point, since this point just in sy is equal to 0.5, so if you just use this point as the input for f of sy, the return value will be 0.5, right? So as sy is getting larger, eventually the maximum value will just happen here. Eventually, only this point, they just share the same tangent line. They can have an extreme value. 大家想一想哈，这边是这边是0.5经过的，这边是1经过的，越远 sy 等于 c 那个7值会越大，对不对？到什么时候它会最大？就是它刚好切过去，跟它切过去的时候会最大，再过去就不可能了。为什么 ？sy 不管你 sy 在这个线上面带什么值，它们绝对不会产生 sy 只能50的，大家同意吗？它绝对会有50的。为什么？50跟它已经没有交集了，所以你找不出任何一个点带出来的值是50。如果 sy 等于100是在这里，它们两个都没有交点，那你找得出这上面的点的某个点带出来的值是100吗？不可能。好，所以呢，在这 case 有交点的，这边有个点，这个有一个点，这两个点带进去，我是不知道它真正的点是多少，不过没关系，这两个点呢，一定会让它的函数值return回来是1，这个会return回来是0.5，越靠近原点值越小，但是我总是可以找到这个椭圆上面的点，让它的return值告诉 sy 等于0。那极致在哪里？最终，你既要它有值可以return回来，比方说我刚刚讲100不可能，50也不可能，只有在什么时候？轻轻的切过去的时候，最极致就在那个时候了，对不对？你想一想，这里是1，这里是0.5，这里应该是1.5。好，刚刚我们偷知道答案了，答案是2。真正轻轻切过去的时候是只有在 sy 的2。再过来，比方2.1的时候，其实它已经没有交点，没有交点代表我这上面没有一个点可以产生的是2.5。所以我有什么？黄色的线跟这个绿色的线 轻轻切过，他们 share 同一个 tangent。This will be the extreme case, right? If the green line just share the same tangent line with the yellow ellipse, their gradient vector will be parallel. Not the same, will be parallel. So you can see for the green line, we can get its gradient. We call it gradient f, right? For the yellow line, we also can get its gradient g. So only these two vectors parallel. So parallel means gradient f should be lambda times gradient g. Then we can get the extreme value at this point. So the gradient vector, for example, in this case, there are 4 possibilities, right? Here also have, here is also have, here is also have. So totally we have 4 points. So totally we have 4 points that can maximize or minimize the value. Okay, so I just use this simple example to explain why, but I cannot say it can represent all, but this is a very good example to show why gradient f should be lambda times gradient g, because only this point can produce the extreme value. 好，那再回来哈，真正怎么算的时候，是大家比较会遇到这只是原理要告诉大家了哈。就我讲的，你要先把这个原理可以让自己有一个直观的想法，那你就比较能够接受它，好吗？那这是计算的时候，当然是大家比较会遇到的状况哈，所以我们就再把这个再讲一次哈，因为这个蛮重要的哈，这个也告诉各位啊，一定会考的啦。gradient这也一定会考的，那你至少要会操作，对，原理用刚刚例子可以加深你的印象，但是起码你要会操作哈。好，那我们再从这个题目再重新看一次。我的目标是要看 f(x, y) 能不能得到极大值，但是呢，我受限于这个曲线上面的点，所以首先呢，你要把 f 跟 g 他们两个不同角色扮演的 f 跟 g 找出来，一个是应该是 xy， 一个是这个，把它稍微调整一下，然后我们就分别算它的 gradient vector， gradient vector 就是 partial f partial x partial f partial y， 然后就得到它的 sy 的向量。gradient g 就是对 g partial x partial g partial g partial x partial g partial y， 我们可以得到它的向量。那这两个向量呢，依据 Lagrange Multipliers， 它必须是平行的。那这里是 s 上面的向量的分量，这是 y 方向的，这是 s 方向，这是 y 方向的，所以这两个就要成倍数的关系。那这个呢，总共有3个变数，有 s 有 y 有 lambda，记不记得这个 Lagrange Multipliers 就是目标你要找出这个 s 跟 y， 这是3个变数，所以它有 z 跟 lambda， 所以你要找出这个 s、y 跟 lambda， 因为这只有2个变数好，所以我们就开始整理了y 等于1/4的 lambda 乘以 x， 那 x 呢又等于 lambda y， 所以我们就把它简化成1/4的 lambda y 减掉 y 等于0，所以把 y 提出来呢 ，y 乘以这个等于0，两式相乘等于0，要么这个0，要么就这个等于0，所以就 y 等于0，或者是1/4 lambda 平方等于1。好，然后我们就分两边来讨论。如果 y 等于0呢，它就得到 x 等于0。好，为什么 y 等于0 ，s 就等于0嘛 ？y 等于0 ，s 就等于0。所以00点不行，为什么00点根本就不在这条 g of x 上面，所以这些就不用考虑了。好，接下来可能就是1/4 lambda 平方等于1这件事情，所以 lambda 呢 lambda 就可能正负2，对不对？那如果以正2来说呢 ，s 等于2y， 对不对？那不要忘了，我们还有那个 constraint function， 所以我们把2y 带进去，整理出来呢 y 等于正1或正1或负1。那 s 可以得到正2或者是负2，所以4种可能性组合出来，总共会有这4种。那最大值发生在什么时候呢？在 x 等于正2 y 等于正1 s 等于负2 y 等于负2。哦，事实上就是这4个点发生在哪里呢？在没有颜色哈，一个在这里，一个在这里，一个在这里，一个在这里。这个是正2正1的点，这个是负2负1的点，那这个是正2负1的点，这个是负2正1的点。那这4个点呢，可以制造出极大值，最大值是2。哦，这2个点相乘是2，这2个点相乘也是2，这个点2个值相乘是负2，这个是负2。哦，所以有这4个情况。Okay, so I can give you a second example. I'm not so sure if it's too much, but it's okay. Maybe on Thursday I can just review the concept again, but today maybe I can introduce another example to you. Okay, another example is we can just apply that if this is a plane, s plus 2y plus 3z is equals 13. This is a plane. And apart from the plane, there is a point 1, 1, 1. So there are actually just talking about projection. We can project the point onto the plane. But you can just also understand that the point to the plane, there are many possibilities, right? For example, here, so you can see if 1, 1, 1 to this point in the plane, the distance is just like this one, right? If this is P1, so this is D1. If this is P2, this is D2. Then this is P3, this is D3. So we have infinite number of points from the plane. So if we want to get the shortest one, for example, how can we just get the shortest one? Maybe here. This distance is the minimum one. How can we get the distance? Okay, so this is the problem. This is the problem. So the problem we can just formalize it as we need to define some function, target function f of x, y, z, and subject to g of s, y, z is equal to 0. Then we can use the Lagrange multiplier Lagrange multiplier. We try to use Lagrange multiplier to solve the problem. Then we can have gradient f should be equal to lambda times gradient g, right? So this is our target. And then using these two conditions, we try to get x, y, z, and lambda. Okay, this is the Lagrange multiplier. So how can we just fit the problem to this one. So our solution is, our target is, we try to get the distance, right? We define f of s y z is equal to square root of any point here, any point s y z, s y z, and 1 1 1's distance. We try to get the distance, right? So we can define the distance as f of s y z as this one, right? This is our target. We hope we can find the minimum distance, as I mentioned here. Different points, we can get different distance, but we just want to get the minimum. We just want to get the minimum. Then subject to that means the constraint to g of s y z is equal to s plus 2y plus 3z minus 13 equal to 0. Because we need to set some constraint, the syz must from the plane, so this is our constraint. 这是我们的限制。syz 要限制于 s 加 2y 加 3z 减13等于0。So right now we have the target function. We also have the constraint here. Then try to get its gradient. But you can see if the function, the target function defined as the square root of blah 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 is hard to calculate. So normally we will just remove this square root. That will not affect our final result, right? But if we just keep the square root, it's hard for us to get the gradient vector. 这边要讲说，我到这边已经定义出来了，什么是我的目标函数？我的目标函数是要看这平面上面的任何一点点 syz 到空间中的111呢，我想要得到它最短距离的点。但是这个点 syz 呢，它会受限于它必须躺在这个 s 加 2y 加 3z 等于13的平面上。好，所以我就设计了一个 target function， 我设计了一个目标函数是这个函数，我希望它最小。照理说，我应该定义成 square root of blah 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 这样的东西，因为距离应该是两点之间的平方和相加以后再开根号，对不对？那目标受限的限制函数呢，应该是长这个样子，也就是在这平面上面。那为什么这边画一个打叉叉呢？因为如果有这个根号在的话，你要算不好算这规定。但是我们把它拿掉，有没有影响我们的结果？没有，因为如果你把这拿掉之后，这个可以拿到极大值、最大值的话，当你开根号之后，它还是它的极大值。我的 syz 可以让这个平方和有极大值的话，开根号之后，对开根号这个函数来讲，它还是一个极大值。所以为了计算便利起见呢，这个根号呢我就不要了。So I just skip this part because that's easy for you to calculate the gradient, then try to get its another gradient vector, and then try to use g of syz is equal to 0. Then you can get s, y, z, and lambda. Finally, you can get this one. Okay, this is the session 8. Session 8 is a little bit complicated. I should admit that. But at least you need to know how to operate. You need to find what is the f function, should be the g of s, y function, then try to use this rule to get s, y, and lambda. Okay? On Thursday, I will go through this solution again. Okay? Okay, let's just call it a day.